All right. So good morning. Thanks for attending this talk. This talk is actually about lab automation, right? So who really cares about lab automation? Why, if you're here and you are an engineer and you're working in labs, you're responsible for rolling out new services, and you're constantly scrambling to patch and manually move cables and equipment in labs, then you probably have a problem that through lab automation can be addressed and resolved. Really, the business driver for lab automation is the ability to accelerate testing and onboarding of new services, building dynamically network topologies without having to patch manually, which is error-prone and definitely time-consuming. Another huge problem in labs is also equipment sharing. Typically, a very expensive traffic generators are siloed in different groups or organizations, and sharing this equipment is actually complex and difficult. Typically does not happen. That's why actually lab automation is relevant, really to increase the velocity and reduce capital expense and overall cut operational cost in lab environment. So I want to first review the basic concept of layer 1 switching. I'm sure everyone is familiar with it, but just to level set, a layer 1 switch effectively operates as a software-controlled patch panel. Once you can connect your routers or switches or traffic generators to a layer 1 switch, and the layer 1 switch effectively allows you to create circuits which can be dynamically modified through software, effectively a software-controlled patch panel. And to do that today, there are actually numerous technologies. Here I list the three most popular, but actually there are more technologies. There are packet brokers, derivative technologies. There are optical cross-connect, and there are media and optical media cross-connect, which also deals with electrical and optical interfaces. Overall, they do the job. Nothing wrong with any of this technology. However, you will find out as you actually try to implement this technology, the flexibility is not there. The ability to actually perform, operate in an environment with high availability, resiliency, also the ability to perform what I call here the DUT circuit sharing, or ability to effectively to, here, DUT circuit sharing, the ability to actually leverage multiple channels across, or a single channels across multiple DUTs, and even extend the layer 1 connection across labs or layer 3 networks, or even labs at different floors is actually not there. Those are typically chassis-based solutions built on custom technology, sometimes also very, very expensive. So what can we really do to improve the situation here? Another point that I want to make is that if you actually look at the technology commercially available from a layer 1 switching point of view, they really have a hard time to keep up with the explosion of Ethernet PMDs and PHYs and PMDs and the diversity of multi-mode fiber, single-mode fiber, copper, direct attach, multi-lane, single lane. Very difficult to find this flexibility into an optical cross-connect, a layer 1 cross-connect, or even a packet broker. One thing we can do to actually start to change and improve on layer 1 switching technology is actually see if we can use whitebox, traditional whitebox technology. Those are commodity switches which operate, of course, their job is not to perform layer 1 switching, but perhaps we can emulate a layer 1 switching with a whitebox. If we do that, just because we use this hardware, immediately we get all the flexibility in Ethernet interfaces. From 1 gig, 200 gig, 400 gig, 100 gig, immediately you get the benefit of having a platform which scales nicely, effectively with your network, because effectively it's the same device you can use in your network. We have full ability to convert a single mode fiber connection into multi-mode fiber, copper into fiber, mix and match all this connection, and even speeds. You can connect a 1 gig port to a 100 gig port and still have effectively layer 1 emulated connectivity. Because these white boxes are normally 1U, 2U at the most, you can actually build a very large scale-out fabric through leaf and spine architecture, and you can accomplish, let's say, scale capacities which are at least an order of magnitude higher than a traditional layer 1 solution. I'll show you a couple of examples in a moment. And while you do all that, you can dramatically reduce the cost of building a layer 1 switching fabric for your lab compared to traditional technologies. So I want to show you now the most interesting part. Yeah, the white box is interesting. It's actually very powerful in terms of hardware platform, but there is software that can also take advantage of this platform and perform what I call it a layer 1 emulation. Of course, you're dealing with a packet switch platform, and you're trying to emulate a circuit switch technology. I call it here for simplicity virtual wire, because effectively we're not really pulling wires like you do in a physical, let's say, cross-connect, or in a physical layer 1 cross-connect. What we're doing here, we're emulating virtual wire. And I'm going to propose two approaches. One is extremely simple. One is more complicated in terms of implementation, but it's a lot more flexible and, frankly, a lot more interesting and exciting when it comes to building a next-generation lab automation. So one is based on the white box hardware. I'll show you how it can be done. And the other is based actually on an IP plus an overlay type of technology. So you end up encapsulating all your DUT device under test in traffic on top of an IP overlay with some interesting properties. Let me walk you through the first example, the first scenario, using a basic white box. And then what you do here is actually pretty simple. This is, let's say, a sample pipeline of an ASIC, a merchant silicon chipset. You have your tunnel termination, your layer 2, layer 3 lookup. You typically have an ingress ACL tables. You have a metering functionality, buffering, et cetera, egress ACL. This is the full pipeline. The trick here to emulate a circuit switch using a packet-based technology is to disable most of these blocks. So the software is supposed to disable, turn off most of these processing blocks in the pipeline of the packet. So what we do in the software, we need to disable, number one, MAC learning. Second, you want to disable any layer 3 routing and switching BPDU kind of processing. On top of it, you need to prevent the CPU of your switch to receive any packet from the network. So the entire control plane processing needs to be turned off. And all the switch is supposed to do is program for port 3 to be connected to port 10, is to program effectively an ingress ACL. And this ingress ACL has a very simple rule which says associate all the traffic coming from port 3 to port 10. And because you have disabled all the rest of the processing, you effectively have already emulated a layer 1 switch. It's a nifty trick which allows you actually to use a white box as a true, let's say, as a quasi layer 1 switch. Of course, there are limitations which I'm going to discuss later on, but at a high level, this covers probably 95% of the use cases. Also, I want to point out that at least the devices we experimented with allows you actually to turn off error frame processing. So you can actually transport CRC packets, CRC error frames, Ethernet frames. You can also transport RAN packets, small packets. So you can really emulate a true wire in terms of transparency even to packet errors. And last but not least, I want to point out something interesting, because this is what actually layer 1 switches do. When port 3 goes down because you disconnect the DUT, you are supposed to send a signal to port 10, and port 10 gets disconnected. That's what happens when you open a circuit. Well, in this case, your software needs to, the software running on this white box needs actually to perform this operation of effectively propagating a link failure or a link up-down event to the remote port. So this is a couple of examples of what you can achieve with this. You can achieve full transparency to any Ethernet packets. You have error frames at the top. control packets at the bottom. You can have LLDP packets, BGP, LACP, and different ether types, even MPLS, fiber channel over Ethernet. All sorts of encapsulation ether types actually can transport it across an infrastructure program the way I described before. Also, very interestingly, from a flexibility point of view, you can actually have a 100 gig port talk to a 10 gig port, a fiber connected to a copper. All these combinations are now possible, and many of those things are not possible actually with traditional layer 1 cross connects. This is an example you can build easily with a 1U switches, with a 1U switch with 32 ports of 100 gig, which splits into, each port splits into 4x10 or 4x25. You can easily build a non-blocking fabric with 2048 ports with 16 spines and 32 leaf switches. So the scalability is actually pretty significant. Just want to show this as an example. So in a nutshell, what do you get if you use a whitebox with a few tricks in software to emulate a layer 1 switch? What you get is a device which is transparent to all kinds of Ethernet traffic, encapsulation, including errors. You get a device which gives you enormous flexibility in terms of mix and matching Ethernet interfaces, any speed, any media conversion. If you're lucky, you get an OS that implements the logic to track effectively the state of a port across the fabric. So you can disconnect on leaf 1 the DOT that is connected to leaf 25, and leaf 25 is supposed to receive a signal that this device, the device has to be disconnected, or there's a link up and link down event. This infrastructure is normally programmable, unlike traditional layer 1 switching. You can use modern REST API, Ansible style automation to actually program this kind of infrastructure. And you also have the ability, if you implement lab automation software, there are a few companies building lab automation software, they give you the ability actually to do end-to-end path discovery across a massive leaf spine fabric. And last but not least, this is a modular pay-as-you-grow design. You can start with 1 device, going to 3 devices, and so on. It's truly modular pay-as-you-grow, unlike a traditional large, let's say, layer 1 switching matrix, which typically come in a chassis form factor. The second more interesting way, a more disruptive way of thinking about building a layer 1 cross-connect fabric is actually by implementing what I call here a point-to-point virtual private wire service. I'm actually reusing, borrowing language from this EVPN RFC, which actually defines how to build a point-to-point transparent link across a BGP and a BGP IP underlay effectively. So here again, what you do is you have your leaf switches connecting to your devices under test. Here you can have your core spine. It doesn't really matter actually what you have up here. This is pure transport of IP packet at this point. And you build effectively an underlay with IP, CMP, BGP. Then here the goal is to build an overlay where the virtual tunnel endpoint sits on every switch, and it allows you to actually create a mesh of tunnels between all the leaf switches. In this case, you can use an EVPN control plane to manage all this. That's an option for sure. But really the key here is having software which can hide all this complexity, right? Because in the end, you're in a lab, you want this to happen pretty much with a point-and-click operation. I'm just disclosing under the table what really is happening under the hood, what really is happening to this infrastructure. But you're managing this infrastructure with the same software that you use to manage a regular virtual wire. The trick here, again, to disable MAC lookup, no learning. You want these links to be transparent to every protocol. Failure propagation is also very desirable here, is actually a must, and it's actually implementable if you look at this technology specified by EVPN. Now, the problem is there are very few implementations today, and even less are integrated with lab automation software. But this actually gives you the full benefit of an IP CMP fabric applied to lab automation environment to build a dynamic cross-connect, layer 1 transparent cross-connect. So in this second scenario, what you get on top of everything I discussed before, you get actually 3 or 4 interesting properties. Number one, and I will actually show you what I mean by that, you have the ability to have guaranteed path automatic discovery between any two DOTs. In a traditional circuit switch environment, even if you provision a fabric with non-blocking bandwidth, I will show you that you can actually end up in situations where you do not have the guarantee ability to discover a path between any two DOTs, which is actually very disruptive. Second, we have the ability to perform dynamic bandwidth utilization. So what this means is you can connect 40 DOTs and leverage one uplink. In a circuit switch environment, 40 DOTs, you need to burn 40 uplinks. So it's a lot more efficient, and you can actually share fabric paths in the fabric, the ECMP fabric, across multiple DOTs. Then, path resiliency and automatic failover. If a spine fails, if a link fails, you rely on an IP fabric to reconverge, right? You have sub-milliseconds reconvergence. It's transparent to the DOT. The DOT will never experience a failure. If today you try to deploy a layer 1 switching fabric, even with fancy orchestration software, if there's a failure, the DOT is down, somebody has to go in and find another path through the fabric. It's very time-consuming and expensive. The way around that, typically I've seen people over-provision the fabric uplinks to have more paths available to reduce the occurrence of failures and oversubscription. Then the last important properties we are adding, again, now we are leveraging an IP transport, right? So these layer 1 circuits are actually traveling on IP. At this point, I have multi-location capability. I can extend this technology across labs. This is unthinkable, of course, in a traditional layer 1 cross-connect technology. Now I can connect 3 labs, 5 labs, 8 labs through this technology and share resources across multiple labs. Very, very powerful. Of course, because now we are encapsulating using VXLAN, there's a sort of we need to be mindful that all the routers in the path connecting the geographically distributed locations must be able to accommodate the MTU adjustment from VXLAN. It's about 50 bytes, okay, extra. So the MTU needs to be factored in. The disadvantage of this technology is that, of course, you're managing an IP control plane. It's not as sort of simple as, let's say, the basic layer 1 switching, but that's also why it's a lot more powerful. Again, the trick, I repeat, if you have integration with lab automation software, which can be homegrown or can be, there are 3, 4 companies actually building these solutions, then you don't really know you're running an IP network underneath. It's all taken care, all automated. You just have to decide which port connects to which port dynamically. Now, let me actually review the 4 advantages of this technology using over a traditional layer 1 switch. This is actually what I call layer 1 path auto discovery with guaranteed connectivity. Here, let's say you bought a traditional layer 1 fabric, right? And what you have here is you have 6 ports down, and then each device has also 2 uplinks. So this is actually non-blocking. Technically, in networking language, this is a non-blocking architecture because you have equal bandwidth leaving the switch as you have serving the devices under test or the edge ports. Now, look at this. A connects to B, right, through the blue path. C connects to F through the green path. And now you want to connect B to E. Well, B can go here, but has no way to reach E. So although you have bandwidth, and this is technically, or let's say, a non-blocking fabric, you end up in a situation with just 6 ports, you cannot find a path. This is actually where people building these things typically over-provision by a factor actually of 2. So the cost explodes. Of course, it can be done. It can mathematically resolved. But the cost of doing this is in complexity and dollars because you need to proliferate number of spines, number of cables, and this is a big problem operationally, right? You cannot afford to have, although you have bandwidth, not to be able to connect to DOT resources. Very disruptive. Now, let's consider the case where we have an IP fabric underneath with our overlay technology on top, with all the tricks and modifications we have done. At this point, A, B, C, D, they will always talk to each other because effectively you're using a packet multiplexing here. You're not building static circuits, carving static circuits like you do here. Here is packet multiplexing. You always find the path to destination. Always find the path to destination. And by the way, this path is completely auto-discovered. You don't need to in this case, you need software to engineer which uplinks you take to reach the remote leaf and the remote DOTs. Here, you let IP figure it out yourself. You just say that you want to connect port A to port E, port C to port F. Any combination is fair game. You let IP then do the job for you. It's extremely more efficient and extremely simpler in the end and lower cost to implement because now you can leverage. You don't need to over-provision to avoid, let's say, path conflicts. Another important point here is the ability. This is actually another massive difference, right? Imagine you're building a fabric like this, right, with a traditional layer 1 switching technology. You want to connect two DOTs. The uplinks are 40 gig in between because you may also have 40 gig devices. Well, in this case, because you need to carve out a circuit end-to-end, you're burning a full 40 gig path to transport 1 gig. Not great. Here, we leverage, again, IP packet switching. So you can have 41 gig ports, ride a single 40 gig channel. Again, this is a much more efficient way to utilize your assets, your links, and effectively you reduce dramatically the number of devices you need to manage. Path resiliency, right? An automatic failover. Like I said before, if your DOT fails or a link fails or a spine fails, anything in the path fails, you're done. It's all about figuring out manually how to reconverge. An operator needs to go there and try to find a new path through this fabric, right? It can be automated all you want, but it's a lot of work and it's manual, right? Here, you leverage effectively ECMP, right? A link goes down, a spine goes down, two spines go down, doesn't really matter. The connectivity is always guaranteed between two devices. So for 90% of the scenario, 95%, this is actually a solution which is very effective, and you can't do those things with a traditional virtual wire or traditional layer 1. This is my favorite, frankly. It's the ability, because now we're leveraging an overlay technology. An overlay technology means we're routing effectively tunneled traffic, so those are UDP packets. I can actually now interconnect the location across any WAN. You can transport IP, then you can transport my layer 1, let's say, circuits, virtual circuit, emulated circuits across multiple locations, and you can share equipment and build a logical topology with equipment which is geographically dispersed across multiple labs. This is sort of a summary of what I discussed today, right? So on the first column, you have the traditional layer 1 technologies. Here we have the virtual wire done with white boxes, and here we have the virtual wire done with an IP overlay. I call it the layer 1 plus. The layer 1 plus clearly gives you the best flexibility, right? You can do automated path discovery, path resiliency, dynamic bandwidth sharing, extend across locations. What you cannot do that easily is actually error transparency. This is actually chip dependent, hardware dependent. Some chips allow you to disable CRC, but actually small packets are very hard to get through in an encapsulated VXLAN scenario, at least for the investigation and analysis we have done. So a little bit of limitation, and plus, if you're conducting wire speed testing, let's say you are a network equipment manufacturer or that has to test high-speed interfaces, then you need to factor in that there's an overhead due to this encapsulation. You don't occur into any overhead in any other technology. The virtual wire, compared to traditional switching technologies, is a lot more flexible in terms of mix and matching interfaces and densities and cost and scale-out capabilities of the fabric you can build, but effectively is a little bit more intelligent version of a layer 1 device. What you cannot do with a switch like this, with a whitebox, for example, is transporting Ethernet backplane, let's say KR type of interfaces, KR, KX interfaces. Because in the end, here is not a layer 1 switch. It's still a packet device, and you're just emulating through the tricks I've shown you before. You're emulating a layer 1 circuit. So it's not truly layer 1, and you lose a little bit of transparency. But again, we're talking about 80, 90% of the applications for which actually this technology can easily replace traditional layer 1 switching technologies. This is the end of my quick talk. I want to open it up. I have 4 minutes. If there are any questions, happy to take on your questions. No more questions? Okay, thank you.